and Peter will speak on contact non-squeezing and Rabinowitz Floer homology. Thanks very much, Peter, for giving that talk.
Thanks for the introduction. Yeah, it's great to be back. Thanks for the invitation. So I want to talk about contact non-squeezing. I really want to advertise a theorem, not of mine, of course, but by Eliashberg-Polterovich, because I think it's a great theorem. I give a slight different version, which they jointly did with Kim then. But I want to just start with something really simple. But so here's a starting point, at least of a little story. You can study the standard contact space. So you have psi is the kernel of the one form alpha. Alpha is, so my coordinates in here are, there's q's, n of them, then there is n p's, and then there's a special coordinate z, that's the +1 coordinate here, and then alpha is just dz plus some qi d pi, pi d, that doesn't matter really, but pi d qi. Okay, this is a standard contact form on R2n plus 1, and it has a nice, so for any row non-zero real number, we have a nice contactomorphism, namely phi rho of, and let me just write q, p, and z, and think of q and p as a vector, right? It's just, you just multiply q and p with rho, and then z with rho squared. So then you get phi star, or phi rho star alpha is rho square alpha, right? It's a trivial computation. So it's in particular is a contactomorphism. And what does it do? Well, it does something interesting, namely, so for any R1 and R2, you find a row such that phi rho maps the ball of radius R1 into the ball of radius R2. No, because what does this thing do? It scales just the coordinates, while the z coordinates is scaled in a by different amount, but doesn't matter, right? So if you want to get something small, you get something small. So, and if you want, you can call this contact squeezing. It's sort of squeezing in the worst possible sense, because you get any large ball and any small ball. And of course, the remark is compare to Gromov non-squeezing. Yeah, it's much worse. Not only is so we know symplectomorphisms not only preserve volume, but much more. Let me just say here, but are much more rigid. So if you do the naive attempt to do the same thing in R2n plus 1 in the contact world, you miserably fail. Yeah, what does Gromov non-squeezing tell you? You can't get a large ball into a small cylinder. In particular, so getting a large ball into a small ball with the symplectomorphism is trivially impossible because of volume constraints. So Gromov's non-squeezing is much larger, but in the contact world, you don't even have a volume constraint. Mm-hmm.
So you're saying you can squeeze it in, preserving the hyperplane.
Right. This is a contactomorphism, right?
But contactomorphism means preserving the hyperplane.
Yeah, contactomorphism just means preserving the hyperplane. Yeah, contactomorphism just means phi star psi is psi, right?
This thing does not preserve alpha.
No,
but
right.
Okay, but suppose you require it to preserve alpha.
And but that's a bad category of maps.
It's in symplectic geometry you actually require to preserve form.
Right, but that's a different story, because you don't want to preserve if you preserve the one form, then you're basically talking about symplectic maps. If you take, not quite. But the point is, in the symplectic world, you can't rephrase the question in the same sense. Yeah, you can't. What do you want to preserve if you don't preserve the form? If you want to say you preserve the form up to a function, then the function is constant anyway. So you're talking about symplectomorphisms again.
So suppose in this case I asked about preserving form.
Yeah, but that's, yeah, you can of course do that. Then you get, of course, it's trivially a volume constraint, but it doesn't, that's just the wrong category of maps if you want to study the contact world, right? Yeah. So I'm just saying that I'm just saying the naive attempt obviously doesn't work. I'm not making a big point here. The big point is a theorem which comes now by Eliashberg-Polterovich, that you can still have contact non-squeezing in the right setup. Okay, so, right, let me tell you how this goes. So the next attempt is, and let me just say let's get rid of the phi rows. And how do we do that? We just replace R2n plus 1 by R2n cross S1 with same contact form. Okay. So then, obviously, these maps phi rho won't work anymore. You can't just rescale because now the z is the coordinate on S1. Okay, so where do I write this? So then, in this situation, yeah, let me just write down the theorem. There's this great theorem by Eliashberg-Polterovich. From 06, which tells you the following. The first statement is, if there exists a natural number such that your two radii, R1 and R2, they are separated by this integer, so if, then there exists no phi in cont 0 of R2n cross S1 mapping the big ball. And what is the big ball now? With phi of, we take the 2n dimensional ball of radius R1, cross it with S1, and we want to map it in the small ball, well, in the other ball. Okay? The little important thing is here the sub-zero. That's I'm not so yeah. So there has to be contact isotopic to the identity of the phi. Okay, so this is non-squeezing. Oh, now it's non-squeezing. Huh? You can't get the large ball cross S1 into a small ball cross S1. Okay, if they're separated by an integer. Okay, that's the first part of the theorem. B, if R1 and R2 are smaller than 1, then there exists a phi who does the job. Okay, so if this is non-squeezing, then this is squeezing. So non-squeezing and squeezing, in a sense, coexist. Yeah, so for radii which are separated by integers, you can't squeeze a big ball into a small ball. If I'm saying big ball, I always mean big ball cross S1. And if the radii are small, then you can do whatever you like. Okay? If R2 goes to 1, I have to remember.
I'm thinking about like the limit. Like, let's say you have this embedding.
I think you can't anymore. In the limit, you cannot.
Suppose you take a sequence of this embedding.
Yes.
What happens to this embedding?
You probably go to the closure or something like this. I'm not quite sure. Yeah, I'm not entirely sure what happens in the limit. I mean, maybe they just don't converge, right? As maps, of course, you can. No idea. I never thought about I'm actually much more concerned with part A. So I never thought about what happens. I can't prove part B. Or I can't understand it really either. I mean, it's just a construction. You can just read it. I mean, and then you can. This is explicit. This map is explicit. This phi.
But this is not a complete opposite with our statement.
No, it's not. No.
Something in between.
There's plenty of questions in between. Yeah, and there are announced results that something that actually the moment you are beyond one with one of the radii, that no squeezing exists anymore, no matter if they are separated by an integer or not. But at least I'll explain you later what my take on theorem A is, part A of the theorem is.
So does theorem A fail for removing sub-zero by like wrapping multiple times around the circle?
By removing, say that again?
By wrapping multiple times around the circle? Or how does it, like, are there counterexamples known when you remove the isotopic to the identity?
Oh no, yeah, then you can. Yeah, I have never thought about that, but then you probably can take covering maps on the S1 thing, yeah, because some of these phi rows survive, right? If these are compatible with taking the mod 1, yeah. Okay. All right. So this is the squeezing part, and then the last part is, I mean, they didn't state it as one theorem, but I want to add it as part C. So we're always talking about the 2n ball there of different radii, but so let's take the standard ball. The boundary of that is the standard sphere. This is non-orderable contact manifold. Let's make this a sentence, is a non-orderable contact manifold. Okay, and an important term is this non-orderable. So let me make a few remarks about this. So number one, the first remark is, in A, if you want to prove a statement like A, you need obstructions. You need some invariants. So you need obstructions to say, well, that such a map can exist. B is a construction that is actually implicit, so you can just write down the map, which just does it. And so about C, let me just explain to you what non-orderable means. At least an equivalent condition. A contact manifold sigma alpha is non-orderable if there exists a very special contact isotopy. So if there exists a contact isotopy phi t with, okay, right, so phi t is a contact isotopy, so phi t is, all phi t are in cont 0. It's a loop, so phi, whenever I write something like this, phi 0 will always be the identity, so if I don't write it, assume it. But this thing is a loop. It's a loop of contactomorphism. It is a positive loop, so the corresponding contact Hamiltonian is just you take the generating vector field and apply the contact form to that. And then you get a function that I usually call ht, and that's a function on sigma, and it takes only values in the positive real numbers. So the contact Hamiltonian is positive. Okay, so we have a positive, this thing is called a positive loop, and the last property is phi is contractible. In let me say it's through contactomorphisms. Okay, so this is orderability, non-orderability, and the thing is called orderable otherwise. Okay, that's a concept introduced by Eliashberg and Polterovich in 2000 in a really great paper where they actually proved that their definition of non-orderable is equivalent to this statement. Okay, so don't take this as depends on what you know. If you know the definition, then this is a theorem. If you don't know the definition, then this is a definition. And why do I write this? So what has it to do with A and B? It has mostly to do with B, namely, I don't want to explain how it really works, but let me just say that in this paper by Eliashberg-Polterovich from 2000, they show there's a strong link between orderability and squeezing. Okay, I'm sure nobody can read that. So there's a strong link between orderability and squeezing. So the fact that you can squeeze a ball cross S1 into a smaller ball cross S1, that is because the boundary of that ball is non-orderable. Okay, so that's what is explained in their paper. And in fact, it's explicit, as I say. So you just on the sphere, actually on on all odd spheres, you can just write down explicitly this loop. You can write down the contact Hamiltonian, and then you can write down actually the squeezing thingy over there. Okay, so it is in a sense very explicit, though the link is still sort of mysterious in a sense. Okay, but there is a link. Yeah. Other way around. If it's non-orderable, then you have infinitesimal squeezing in a sense. So if you take, okay, it's more like a meta statement. But for instance, similar things are true if you replace the ball by. So if the ball lives in R2n, if you replace R2n by a cotangent bundle and take a small neighborhood of the zero section, and then infinitesimally, so tiny neighborhood into an even tinier neighborhood, it's not possible because unit cotangent bundles are orderable.
One more question. How significant is the contact structure? I mean, can I make it more flexible, make it like almost contact? Do you really use alpha h to the alpha to the power and is the volume?
Yes. Yeah, because I lift everything. So the next thing, the first thing you do in the proof is always lift everything to the symplectization and make it Hamiltonian diffeomorphisms with the symplectic form. So you really need the rigidity of symplectic structure. So if you just make it almost contact, then if you lift it, then you do have a. Yeah.
So Peter, the proof of these results relies on some theorems in the symplectic category.
Mm-hmm.
When you say you lift these two, so you're
Right.
using some machinery from the symplectic category.
Yeah. In fact, I'll explain you my understanding of theorem A, of part A, and you probably won't see immediately, but I can tell. I mean, it's really the first step in the proof you do is lift everything to the symplectization, make it into Hamiltonian or symplectomorphism, and then think about it like that. I think it's a quote of Leonid's. He cannot think about contactomorphisms. He always thinks of them as he just immediately lifts them to symplectomorphism. I don't know whether that helps, but okay. All right. Okay. So now. Now, what I want to tell you about what Will and I did is I need to tell you one little piece of setup, but that's very simple, and then I give you a theorem, and then we discuss consequences. So the setup is as follows. We assume that our contact manifold is Liouville fillable. I.e. there exists a symplectic manifold W in an exact symplectic manifold compact with sigma is the boundary of W and alpha is the one form restricted to the boundary. So exact. It actually will be slightly non-compact later, but I'll mention that when we come to this. Okay, so that's what we assume, and it's clearly true for the ball. No, it's clearly for the sphere. What I wanted to say. The sphere here is the boundary of the ball, and everything is fine. Okay, so that's the assumption I want to make. And the point is, that's the other word in the title. In this situation, you can assign. Let me just say an invariant, which is called the Rabinowitz Floer homology of this pair W and sigma, and it really depends on W in general. And this is a For our purpose, it's just a Z mod 2 vector space. Okay? So whenever I have a Liouville fillable contact manifold, I can assign this invariant Rabinowitz Floer homology. And this was invented by Kai Chilibak and Urs Frauenfelder. Okay, and then you can assign this invariant. That is, for our purposes, it's a Z mod 2 vector space. It has, of course, lots of other structures, but for our purposes, all we want is a Z mod 2 vector space. And then for a while, I want to work under the following assumption. Assumption A will have slightly stronger assumptions later. The assumption A is just the assumption that R of H of W sigma is not the zero vector space. Okay? And that is not true for the sphere. Okay? The sphere is not an example. But this is at least a very, so there's, let me just say here, there's tons of examples, many examples. And this is a checkable condition. So by now we can compute an R of H fairly well. So in particular, we can decide fairly easily whether it's zero or non-zero. Okay? Okay, and so one piece of notation, let's call P cont 0 sigma is just a path space of cont 0. So it's just a set of contact isotopies. Yeah, what is the so an element phi here is just an element in this path space, just a path of contactomorphism based at the identity. That's all it is. So phi 0 is the identity. Okay, so under these assumptions, so that we are working with the Liouville fillable contact manifold, and that this R of H is non-zero, we have the following theorem. So there exists a map on this path space to the real numbers with the following properties. Okay, so this list is not quite complete, but I give you quite a number of properties. So the first property is if you have two contact isotopies which are equivalent, and here that just means is homotopy rel endpoints. Yeah, so you have two paths, both start of the identity, both end at the same thing, and you can homotop from one to the other. And if that is the case, then C of phi is C of psi, i.e., I could have said it differently, C descends to a map on the universal cover. Okay? Yeah, so this equivalence relation is exactly the equivalence relation which gives you the universal cover, right? But for my purpose, it's important that C is actually defined on individual paths of contactomorphism and contact isotopies, but it depends only on the class it defines in the universal cover. So 2 is easy but important. You take the identity, you get 0, so that's just some normalization property. Then 3, it's well behaved with respect to the C0 topology on contactomorphism. So C is Lipschitz with respect to the C0. Let me just say, with respect to the C0 norm of the contact Hamiltonian. Yeah, so for each path of contactomorphism, I can, just by this recipe here, I can define can assign the contact Hamiltonian, and the contact Hamiltonian uniquely specifies the path. The path. So there's a one-to-one correspondence between contact Hamiltonian and the path. It's different than in the symplectic world, right, where you take d of h and then turn that into a Hamiltonian diffeomorphism. There's no d. So if you know the little h, you know phi t, and if you know phi t, you know little h. And so if you have a path and you change the path and the C0 norm, you should compute the contact Hamiltonians, then the C just changes in a Lipschitz way. Okay. We have a triangle inequality, meaning this inequality. So I think of this as a triangle inequality. Yeah, so I can compose path, yeah, just pointwise. So this for every t, this is the path at time t is just phi t composed psi t. Okay, and then you have this rule, and I think of it as a triangle inequality because it really becomes the triangle inequality for a metric later on. Okay, for 5, so far we can take the zero function, right? Yeah. So we need some property which makes this map C non-trivial, and here it is. So if phi is generated by ht with, so now we have two cases. First case is ht is, and now the signs are slightly odd, but I can't do anything about it. If ht is strictly negative, then C of phi is strictly positive, or ht is strictly positive, then C of phi is strictly negative. Okay, so we get, now it's non-trivial, the map. And now we get a relative version of this last property. So last statement is, what's the number? 6. If I now assume just that the contact Hamiltonian restricted to the support of phi t is strictly negative. Yeah, so support is just, this I want this for all t's. The support just means the points where it's not the identity, and then take the closure. If it's strictly negative, then C of phi is strictly positive, and here comes, now this is important, and if the opposite inequality is not strict, if I assume that I'm strictly positive on the support, then all I can conclude is C of phi is less or equal than 0. Okay, and here equality happens. What I mean by this is you can't do better than that. So I can, you can take, it's basically the triangle inequality with some geometric arguments show you that if the support is tiny in a certain sense, then this will always be less or equal than 0, even under this condition. So the best thing you can say is less or equal than 0. So you can produce examples where it's actually 0, even though we have this condition. Okay? Yeah? You look confused.
So the first line is 6. What if
Yeah.
BT is like the trivial isotope B?
But then HT is also the HT is 0 then. Right. So if phi t is a trivial isotope, then this is an empty set.
Yes. So you're saying except in that case, this is true.
Oh yeah. All right. So yeah, good point. So this statement only makes sense if phi t is not the identity all the time. Right. So otherwise you of course contradict number 2. Right. Okay. Yeah. But otherwise it's an empty statement. Correct. But okay. So let's assume. Actually, that's already true here. So in 5 and 6, you have to assume that phi is not the identity. Yes. Thanks. Okay. Okay, that's the statement. And I wanted to add something little here. Yeah, okay, I'll add it later if I need it. Okay, so now that's the theorem. Okay, you can find a map like this. under these assumptions that you're Liouville fillable and that R of H is non-zero. In fact, if R of H is zero, you then can still define the map C, but it's constant minus infinity. Okay.
Do you prove this theorem also going to the symplectic category?
Yes.
I see. So in the symplectic category, what comes into it? Is this related to some capacity or some sort of?
No, it's the other way around. Actually, we're going to turn this C into a capacity in a little while. It's something like a capacity. No, but what comes in is really R of H. R of H is something which lives in the symplectic world. So what you do is, the picture is really, you have sigma somewhere and then you have the filling. Here's W and sigma is this boundary, right? And under these assumptions, you can always attach here sort of the positive half of the simplexization to this. And then you're working in this non-compact symplectic manifold. And if you have a contactomorphism phi t, the moment you have an isotopy, you have a unique way to lift it to the symplectization as a Hamiltonian diffeomorphism. And then you just hit it with symplectic methods there. Still, the situation is special in the sense that, well, there's sort of a technical detail, but it is important in this, if you're working in the symplectic world, that these things come from a contactomorphism. So that's sort of reflected even, I mean, this information is not lost. So you can't say I have the same statements for Hamiltonian diffeomorphism in this non-compact symplectic manifold. That's not true. That's important. Okay. All right, so this is a theorem, and it's probably not very interesting, so let me tell you why actually I think it is interesting. So let's talk about some consequence of the theorem. So let's start with some fairly straightforward. Okay, so since I just erased it, the next thing I want to talk about is orderability. So remember, orderability is you have a loop which is positive and contractible. That were the 3 points, right? So a manifold is non-orderable if there exists a positive contractible loop of contactomorphisms. And the first thing is we'll deal with this. Okay, so some corollaries. So first corollary. So we're always working on this assumption A, right? So let me just write it once. But assumption A immediately implies sigma is orderable. And this gives a huge number of new examples of orderable contact manifolds. Why is that? It's an immediate consequence. So assume that phi is a positive and contractible loop of contactomorphisms. Okay? So that if you have such a loop, then the manifold is that's equivalent to being non-orderable. So let's assume it's non-orderable, thus we have a loop, and now we derive a contradiction. So so it's positive. Positive meant precisely this condition here. This condition, HT is positive. So by 5, theorem point 5 implies C of phi is negative. Okay? Positive loop meant the contact Hamiltonian HT is strictly positive. So by theorem number 5, assertion number 5 in the theorem, you get C of phi is negative. Okay. So then phi is contractible. That just means phi is equivalent to the identity as a loop, where this equivalence relation is precisely the equivalence relation of 1. So by 1, we get C of phi is C of the identity, and then by 2, we get this is 0. This is a contradiction. No? C of phi is strictly negative, and C of phi is 0. So it has to be orderable. Such a loop cannot exist. Incidentally, that's a very good thing, is it doesn't, you see, we use contractible essentially here, right, in the argument. So there do exist examples of Liouville fillable contact manifolds where R of H is non-zero, which carry positive loops, but those are non-contractible. Okay? It's actually very easy to write things down, as one does it. Okay. That's the first corollary. So you immediately get that all these things are orderable, and so that you get a large class of new orderable or of manifolds of which you know that they are orderable. Here's a corollary in the opposite direction. If you assume that sigma alpha is non-orderable, and W is a Liouville filling of sigma, then R of H R of H of W sigma is 0, or also the symplectic homology of W is 0. Yeah, and proof is trivial. So R of H non-zero, this is really assumption A, together with the Liouville fillability. So then this implies, by the previous corollary, sigma is orderable. And this vanishes exactly when this vanishes. Okay? So in particular, here's an example. We know the sphere is non-orderable. So the example is symplectic homology of W is 0 for all Liouville fillings of the sphere. They were actually known, but for all Liouville fillings of S2n plus 1. No. That was known by, it's an argument by Ivan Smith. It's in the biased view on symplectic homology paper by Paul Seidel. He explains how that goes. But this works sort of more generally if you want. Incidentally, now you sort of actually if you really look carefully, you should protest here, because here?
No, the third line from
Third line on this board or that board?
the other one. The homology is non-zero, and then A assumption A, and then it implies what?
Where to look? Here?
Proof,
In the proof. R of H non-equal to 0 is the same as assumption A, and then this corollary implies sigma is orderable. This assumption A implies sigma is orderable. Okay, yeah, sorry. Okay, so here you should protest about this last statement here, because here's S1, and of course if you fill S1 by the disk, then symplectic homology vanishes, because symplectic homology of R2n vanishes. But nobody prevents me to fill it like this. And now I leave it to you to check that symplectic homology does not vanish. That is because only the simply connected spheres are orderable. Okay, so it's I just said the spheres are non-orderable. Only the simply connected spheres are non-orderable. S1 actually is because its RP1 is orderable. So life is good. Okay, that was the first corollary. Let's get some more corollaries out of the theorem. And then I'll tell you how all this is connected to the non-squeezing theory by Eliashberg-Polterovich. So what's next? Oh yeah, here's another little corollary you can deduce. So if you assume that C of phi is negative, or if and now I need to make the addition I forgot to mention earlier, or if HT restricted to the support of phi t is strictly negative, then phi, then I should have said let phi be a loop of contactomorphisms. We start with the loop, and we assume that either the C of the phi is negative or this condition on the loop. Then phi is of infinite order in pi 1 of cont. Okay. So we can detect loops of infinite order in pi1 of cont. So also follows immediately. For instance, let's start iterating the loop, and let's see what we get. So by the triangle inequality, 0.4 up there, you immediately get this is less than nu times c of phi. So this is, if this is negative, so if you assume that c of phi is negative, then that means c of phi nu is negative for all nus, for all iterations. In particular, it cannot be contractible, because otherwise you had to get 0, right? So this implies by 2 and 1 again, phi to the nu is not contractible. That was the first case. The second case, now I have to make a slight addition to the theorem. This is actually true. Here more is true. Here, which is is it the first one? Yes, this one. So here slightly more is true. You can say then we have 0 is strictly less than c of phi, strictly less than c of phi square, strictly less, and so on. So this is actually a strictly monotone increasing sequence of real numbers. Okay? And so then you can take the second case. You just say c of phi, you know, it's exactly the assumption we need, right? So then we know this is less than c of phi squared, is less than c of phi cubed. So again, with 2 and 1, phi to the nu is not contractible. Okay, right? By the same reason. Okay, so these are just some sample corollaries you get immediately from few of the properties of these maps C. Okay. So now I want to make a connection to the non-squeezing results. So we add an assumption to our situation and see what we gain from that. Actually, no, I think we don't need the theorem anymore. Okay, so let's add an assumption. So this will be assumption B. This is assumption A plus. So assumption A was Liouville, sigma is Liouville. So sigma is the boundary of W, W is a Liouville filling, and RFH of W sigma is non-zero. That is assumption A. And plus, we want that alpha, the contact form, is, well, we call it periodic, might not be the best name, is periodic, i.e. if theta t is the rate flow of alpha, then theta 0 is theta 1 is the identity of sigma. Okay, so this is certainly a restrictive assumption. So we assume that the rate flow is purely one periodic, okay? And think of the round sphere. Yeah, wherever you start on the round sphere, you follow the rate flow, you come back after time. Now depends on your conventions, 1, 2 pi, whatever. Okay, so this assumption is certainly more restrictive, but so there are not so many examples, but there are still many examples. It's certainly way more restricted than the previous example, but you can take many examples where this works. So there's not quite so many examples, but this is still very verifiable. So you can easily check whether this assumption is correct or not. So then in this situation, what we do is the following. We set C bar of phi to be take the next largest integer of C of phi. So I'm going to I'm going to call this the integer part. It's of course not the integer part. It's integer part plus 1, but I'm still going to say integer part. Okay, so we just take the integer part of C of phi, and it has the following reason. This is inspired by work of Margarita Sandon, but it has the following nice implication in this situation, namely C bar is conjugation invariant. C is not. And C bar is conjugation invariant only under the additional assumption we make here in the periodicity. Yeah, so that just means if you take a path and just conjugate it, you don't change the value of C. Okay. Yeah, take the satisfying assumption B. So the easiest example to think is the take the round sphere as a Riemannian manifold. Take its union cotangent bundle. Okay. There's many other examples. You can take prequantization spaces, but then you have to replace the filling you don't take the standard filling you get from the prequantization bundle, but you replace the filling by something else. Then you can have more examples of that. But we will be very much interested in non-examples of that, but very close. Namely, things of the form M cross S1. Think of ball cross S1. And the Reb flow will go around always the S1. And the point is these things are non-compact. So sigma here still should be compact. But you, sort of morally speaking, almost all I'm going to say is true for this situation, where you take a nice non-compact symplectic manifold here, exact, cross it with S1. I'll explain it in more detail later. And then the Reb flow will always go around the S1. And then you can set things up so that assumption B is precisely satisfied. And that then relates back to the don't squeezing in a second. Okay? Yeah, but if you want a strict example, take the unit cotangent bundle of the round sphere. Okay, so why is the conjugation invariance nice? Because that comes back to what I mentioned earlier. Now we can build a capacity, something like a capacity. So for U in sigma open, we set C bar of U to be the supremum of all C bar of phi, where the support of all phi t's is contained in U. Okay, so that's a definition, and the corollary. Actually, maybe I should write it here. The corollary of the theorem is then C bar of U is a contact invariant, meaning C bar of psi of U is C bar of U for all psi in cont 0. Okay? It's really a trivial consequence of conjugation invariance. If you write down if you just translate what that means, this equality in terms of the definition, you immediately see is equivalent to conjugation invariance, more or less. But conjugation invariance immediately implies it. Okay. So and then we can use this capacity, or I mean, it's not. I mean, I'm not claiming that it's really a capacity, but it's sort of a capacity-like thing. We can formulate an abstract non-squeezing result in contact geometry with help of these capacities, and then we do an example and recover precisely what we had before in the theorem by Eliashberg-Polterovich. Okay, so then here's it's how do you want to call it? Yeah, let's call it a corollary, really. This is the abstract. I think of it as an abstract non-squeezing theorem. So setup is as follows. We take a nested set of open sets, U and V, and we ask the question: Can we get V squeezed inside of U, right? And let's assume we can. So and phi a contactomorphism such that phi maps the big set inside the smaller set. Then they have the same capacity. Okay, so that's the abstract statement. This is also trivial to prove, but it's very illustrating, I think. So let's do this. So let's start with C bar of U. So U is a subset of V. V is larger, so that means this supremum you're taking in C bar of V is just a bigger supremum, just a supremum of a bigger set. So you get trivially this inequality. Okay, so this follows from U sitting inside of V. Okay, now we use our previous corollary. C bar of V is a contact invariant. So that means this is C bar of phi of V. That's a previous corollary. And then we just use the same argument again. Phi of V is contained in U, so this thing is less than C bar of U. So you have to have equality, right? And it's really important to point out that we take this C bar. So the C is not conjugation invariant, only the C bar is. So here's an example. It's not strictly speaking example, it's sort of. So I just say we may take sigma to be, and that's really true. So the statements continue to hold. If you take sigma to be M cross S1, M d gamma is a Liouville manifold. Oops. And the contact form you put here is gamma plus d tau. Tau is the S1 coordinate. Okay, then you can see the Reb vector field is just the vector field which points along the S1. So the Reb flow goes always around S1. So this is a periodic contact manifold. It's not quite Liouville fillable because, of course, a Liouville manifold, this M is non-compact, so this sigma is non-compact. So formally, it violates the definition of Liouville fillable. But let me just draw you the same picture as before. If you take M cross, here's S1, then this is really the boundary of M cross, and then we take this filling. Okay, take this torus with a little hole in it. And again, this is not compact, so it's not strictly speaking a Liouville filling of this contact manifold. But for our purposes, it is. I mean, yeah, you can make everything I said work in this situation, and if you compute R of H in this situation, it's non-zero. Okay, so it's in a sense it satisfies assumption B. Okay, let's see what we get. Yeah, so the statement is everything works. I said that already. So what do we learn from this situation? In this situation, these capacities C, they become suddenly computable. So the capacities, or C bar, I should say, C bar becomes computable. In this abstract setting, yeah, well, C bar is C bar, but for instance, if you take M to be R to N, and we take U to be the ball of radius R cross S1 in sigma, sigma now is precisely R to N cross S1. This is exactly the setup of the Eliashberg-Polterovich theorem. Then the C bar of let me just write it, BR cross S1 is just the integer part of R. Okay. So in particular, if there exists an integer k which sits between two radii, then C bar of the small ball cross S1 is strictly smaller than C bar of the large ball cross S1, right? Because the integer part of R1 is less or equal than k, but the integer part of R2 is strictly larger than k. So no squeezing. Okay, and this is precisely Eliashberg-Polterovich, but these capacities are in a much broader situation, in a sense, computable. So yeah, let me make this remark real quick. So what you can do is you can just do some symplectic stuff on this manifold M, on the symplectic manifold M. Yeah, our contact manifold is sigma is M cross S1, but if you work with Hamiltonian diffeomorphisms, say Ft Hamiltonian diffeomorphisms on M, and everything is compactly supported, then you can also define these numbers Cm for F, for this path Ft. In a similar, well, I didn't tell you how to define them, but of course, I mean, these things were first, and they go basically back to Viterbo. There's these spectral invariants, they're all over the map in symplectic geometry. We can define these guys, and oh yeah, one remark. These are trivially conjugation invariant in the symplectic world, because the symplectic action functional, which is sort of in the background here, is conjugation invariant in a certain sense. So proving conjugation invariance here, it's a no-brainer. It's a one-line computation. And so what you can do is you can lift phi Ft to phi t in cont sigma, which is M cross S1. So whenever you have a set of Hamiltonian diffeomorphisms, you can just lift it to contactomorphisms. In fact, they're exact contactomorphisms, so they really preserve the alpha. So just write down what the condition is, and then you see what you need to do to lift them. And then the theorem you can prove is that, in fact, Cm of Ft is precisely C of phi t. And, okay, so if you use that, then from that, okay, let me put it in the same theorem. From that, you can then also prove if you take O in M open, then Cm of O cross S1, if you take the corresponding bar version here, is you take Cm of O. Cm of O is precisely defined the same, defined in precisely the same way. You take the supremum over all Hamiltonian isotopy supported in O. Okay, and this is precisely C bar of O cross S1. In particular, for all these sets, you can compute these capacities in terms of the symplectic capacities, and that's actually how you get the ball, and you get a very good handle, at least you get a very good handle on these. So in that sense, these capacities are fairly computable, and you can now cook up tons of other non-squeezing results if you like to. You can also take other capacities if you want to. You can take the Hofer-Zehnder capacities on M and translate that into non-squeezing results. But okay, there's tons of that. So let me take 1 minute. I just want to say you can do one more thing. You can take cont 0 tilde, and you can. So now we have this map to the integers, namely phi goes to C bar of phi. And if you do instead this, so we take C bar of phi plus C bar of phi inverse and take the absolute value, then this gives rise to a conjugation invariant norm. Yeah, conjugation bullshit, biinvariant norm. Okay, so you can play further games, and then if you want to prove for this, so this number here is the distance of phi to the identity, and then you extend phi. So you take the distance and just to the identity and turn it into a real distance. And then if you check for this distance, if you want to prove the triangle inequality, exactly what you need is what I call triangle inequality. That's where the name comes from. Okay. Yeah. Thank you very much for your attention.